Section 23.8, the mixed claisen condensation. When we try to do a mixed claisen condensation, there's a challenge here. So we could imagine taking this molecule apart along that bond, and it would give us a claisen condensation of these two components. Now, that looks like a nice disconnect, but as we've seen before, if we attempt to do the reaction with ethoxide, of course, we'll call this A. A can condense with itself from its enolate, B can condense with itself from its enolate, and so there are multiple products. There are 4 combinations, as we saw before. You draw those on your own. And just as we saw before, there's a solution to this where we use only one enolizable reactant. So what are some of the things we can use? Well, they have to not have an alpha proton. So what would things like that look like? Ethyl benzoate. Right? There's no alpha proton. Ethyl formate. Right? There's the formyl. There's a hydrogen attached to the carbonyl, but there is no alpha hydrogen. And one that's actually especially useful, readily available and accessible, is diethyl carbonate. So let's take a look at how we might be able to make use of some of these. A typical example would be to I'll take the ester we were starting with there. If we react that with well, let me not introduce that yet. I'll put that at the end. We can do these in a mixed manner. So with diethyl carbonate and ethoxide, you get a diethyl malonate derivative. Okay, now we couldn't directly put an aryl group on diethyl malonate in the malonic ester synthesis, for instance, because it's not susceptible to SN2 substitutions. But using diethyl carbonate, we can actually make this substituted with an sp2 carbon here at the phenyl group. So let's look at a couple more. Turns out where this is really fun and interesting is I don't have to limit my reagent to an ester. I can use a ketone, for instance, and if I react it with diethyl carbonate, as above, again with ethoxide, So that puts the ester functionality on the alpha position next to the carbonyl. And we'll see, this is one of the places that this reaction is very useful. So for instance, I can now take this, and with its very acidic proton, with ethoxide, first I can deprotonate it, and that'll go essentially quantitatively. Then I can put in an electrophile like benzyl bromide. If I, and I'm going to turn it around because I didn't leave myself room, I can then benzylate that position. Now, we can bring to bear the chemistry that we've learned before. If I treat this with acid, it will hydrolyze the ester. Following that, by heating it up, it will decarboxylate, and I get the mono-substituted system in a controlled manner. Now again, this allows us to get control of reactions that otherwise can be problematic. Because even with LDA, when we try to make the mono-substituted product, there can often be exchange, and we can get dye or even higher substituted materials. Where this is really cool is in the reaction, say, of this compound. Now, because of the methyl group substitution on this side, the step that makes the claisen condensation irreversible is not present here. So if we react this with ethoxide and diethyl carbonate, we get reaction to form that compound, but of course under the strongly basic conditions, it's deprotonated to drive the reaction. Then we can come in with another electrophile, say allobromide, this gives us a controlled substitution only on the side where the carboxylate is. Then again with first acid and then heat, we can decarboxylate and selectively control the substitution away from the methyl group. Now this is a multiple step process. You have to put carbons and oxygens and atoms in, and then you take them out, and that's not what today we would call an atom efficient reaction. We don't want to put atoms in and take them away and lose them. And atom efficiency is one of the leading edge areas of research for organic chemistry, but it's still a very powerful methodology, especially before the advent of some modern techniques.